Well, to be honest, it matters a lot for many reasons, but I will just focus now for one reason, and I will make it focal point, also present code samples in it. Your transactions initiated by your externally owned address can now be atomic, which means you, from your own wallet, can do multiple calls to different accounts, whether they are contracts, externally owned address, and this is all in one transaction. Let's think of a very common use case. When you go to a decentralized exchange like Uniswap or whatever, you want to swap your USDC for wrapped Bitcoin, you need at least two steps. One, to approve the transfer by interacting with Permeter or whatever, and to Uniswap, and then you also need to do the actual transfer, which in the end gonna make you swap your USDC for the wrapped Bitcoin. So you basically need to do two steps. So let's take a look at this. By the way, I'm sorry. I know, like I told you, I'm not gonna make any slides, but this was something I did like on a Friday night.
Awesome.
And it's just README file. Yeah, that's good. It was just a markdown file. So, okay. So, like you have here, like first you need to approve your DEX, which is Uniswap, and this is in this example, for instance, and then you do the actual swap. But now, if you have an EIP 7702, which means your externally owned address is what is called right now a smart account, you can actually, let's explain now. Like, for example, if you have a smart contract, like let's say you have a smart contract that's gonna do this transfer on behalf of you. So you call that smart contract and it does the approve and the swap in the same time, in the same transaction. So let's start it from here. But now if you have a smart account, you cannot think now of your wallet as being the smart contract itself. The question now would be like, how do I actually make my account to become a smart account, to become like conforming with that new standard, the IP 7702? You initiate something called the transaction type 4. This is a different transaction type from the transaction types we do when we interact with smart contracts or when we do some kind of all the cool things we do in Ethereum. This is something now you initiate by like sending this kind of transaction to the Ethereum nodes, telling them, hey, I want my account now to support the concept of having code in it. And this is done by like this is basically the fields, the important fields that you have in the transaction. You have the chain ID, which in mainnet, like which is 1 in mainnet. So it depends. This is of course important because if you do this transaction on mainnet, and if there's no chain ID field in that, so somebody can take that transaction and actually replay it in another chain. So that's an important thing. You have the address. This address is resemble the address of the logic, the implementation contract that you want to be implemented by your externally owned address. So let's say, for example, there is some contract out there, and you're saying, hey, you know, this code in that contract in Ethereum with that address, I want this code to be, you know, like my code, basically. It's like you're shopping, you're taking that code to be in your account. And of course, unknowns to also keep you away from the replay attacks. And in the end, the signature, which is the RSV, like you are signing that transaction. So that's basically what it is. So I'm not intending to actually have a lot of slides. Like I'm just this talk was mainly meant to be something that we are using. Like let's get our hands dirty. Like that's
awesome.
cracking. Yeah. So I will start from here. And believe I'm having already some project. Okay. Okay, so I'm gonna delete all these. I don't need the counter. This is like I'm gonna show you like a clean starting point. So I'm starting from Fortinet. So this is a completely new project, and I will show you how to do this in code. So I'm gonna create some contract. I'm gonna call it minimal vault, and my goal from this contract is to be like the contract that I'm gonna be interacting with. So I will basically do the very simple approve and deposit example. Let's say I'm gonna take it already from here. Whoops. Yeah, you can see my screen, right?
Yes, we can see your screen.
Okay. I didn't want to show this, but yeah, doesn't matter. Okay, so that's just a simple simple vault contract here. My goal is just to approve it and deposit, and it records your balance. That's nothing nothing fancy in here. And then I will create it. This is where the excitement's gonna happen here. So let's say this is an EOA, externally owned address deposit test. I'll also copy parts of it, and then because I don't want to waste time coding a lot of stuff. Let's copy from here. Okay. So naturally it's gonna shout at me, but let's ignore that for now. So what's going on here is we are having this test here. It's like my goal is to send a type 4 transaction, and then from there I can actually do trying to do all the exciting things. Can I explain that? Oh man. So let's go quickly on this. So this is here the test itself. I'm gonna be referring to a mock token, just creating an arbitrary test token ERC20. This can be a USDC, USDT, or whatever on chain. And this is the minimal vault EA deposit, EOA deposit. This is the vault that I'm gonna approve and transfer the mock token to. And as you remember, I want to do that in one transaction from an externally owned address. The implementation here, as you remember, when I send the transaction type 4, I'm gonna go like shopping. I want some code from the Ethereum chain. So basically, this is the contract that's gonna pick the code and put it in my externally owned address. So the setup is simply, I'm just creating an arbitrary key pair, an address and the private key. This refers to the private key. I need this just to sign the type 4 transaction. Here I'm just setting it up. This is a mock token, ERC20. And we have here the vault. This is the subject of my test. This is the vault that I'm sending to the tokens. And finally, here's sorry, I'm funding, let's say here, funding Bob's address. And here here I'm playing the implementation contract. So what is in this implementation contract? This implementation contract just have one function, just does one thing, but it does it very good, which is just deposit in one step. You do the approve, you do the deposit. And remember, this piece of code is going to be in the externally owned address right now. That's according to EIP 772. And this is the exciting part. Like, I want to put this piece in my own externally owned address. So how do we do this? First, we need to sign and that like this function here, sign and attach delegation. This is something provided by Foundry itself. And its purpose is just to, as I told you, like to send the type for transactions. So if you want to achieve that, you extend the type for transaction. There are many ways you can do that. You can use the cast commands also provided by Foundry, but the cast commands are sending an actual type for transaction and send it on chain to the RPC nodes, and it gets processed there. But this sign and attach delegation is its purpose, I believe, it's mainly for the testing. And like I try to use it for script and maybe try to interact with a Sepolia testnet, but it didn't work as expected. So this is mainly for now, I believe, for test. But you can use a cast, like there is a cast send the type for transaction. You can use that to interact with Ethereum chains, real chains. So this function here, I'm pointing to the implementation address, and I'm giving it the private key. This is not the address of Bob. Like, remember this. This is the private key, Bob, because as you know, I need to sign it. And if you need to sign something, you need to provide your private key. Of course, it's worth noting, I know everybody knows this, but if you're using your actual private key, you need to hide that. That goes without saying.
Don't show your private keys, dudes.
Yeah, definitely. Like, if you're using a real private key, don't do it. Like, be careful. So after that, we need to call the actual function. Now you notice here, this is Bob's address. This is an externally owned address, and I am calling a function against it, as if it is containing code right now. So this function just takes a token and an EA deposit, which is a vault, and the amount that you want to deposit. So let me just let this work. First, you need to install. Let me handle this. First, I need to install. Like, what was OpenZeppelin?
Wow, that's
I think it was, yeah, it's perfect. I still have a good memory. That's fine. Okay, so I just need the OpenZeppelin contracts because, as you see here, I'm using an ERC20, so I need that to be with me. I could have implemented, a generic ERC20. It doesn't need all this heavy stuff. So why is it complaining? Now we need to run this test. I think I will need to do remappings, but let's see that. Yeah, it installed successfully. And I don't think I should need remappings. Let's run it this way. Sorry. Okay. Now I want to talk about something here. If somebody can have a good eye to catch it, I would hope to listen. Like, I'm just focusing on this part here. Like, do you think there is some issue? Because think about it this way. Bob now is a smart contract. Yeah. Somebody speaking.
So Bob is a smart contract, do deposit step,
Yeah.
receive mock
And
token.
I'm calling this function.
Okay, do deposit step, ERC20 address mock token, EOA deposit. What is EOA deposit? Is where the deposit is going to?
That EOA implementation is just like I'm casting it to an EOA implementation to be able to call it this way. It's just a syntactic thing, but I can actually do something like bob.call and send that function.
What comes?
I can do something like this.
What comes to my head? There's no verification if the transfer was successful. But they didn't know if that's the problem.
That would be right if you're doing a call, a low-level call. But in this case, like if it reverts, if this function was meant to revert, it will revert here as well. That's not a low-level call. But the issue actually is more than this. Like if we are talking about a revert issue and we are not checking the success, it's usually when we are auditing, we say like this is a low-level. Like depending on the consequences, it's usually a low severity issue. But in this case, what I'm going to talk about is something really critical, actually, something really serious. Like if you think about Bob right now as a smart contract, some smart contract out there, which is not, he's somebody with flesh, having a private key, having a wallet. Like these are the security implications of 7702. Now anybody can call that function. Actually, it's not only Bob. He's just a smart contract. Somebody out there, like let's say Alice, can just call the code that is coming from Bob's wallet.
That's interesting.
So what do you think? Yes, this is really interesting. Actually, if you know the test, how the test goes, the caller here is actually some address, not Bob. Actually, the caller here is not Bob. The test is I forgot what's the address, but this is like some caller in the Forge test that does calling the contracts here.
I know that this is a problem for other kinds of functions, but would someone else call a function to do the deposit? I mean, I guess that somehow can be painted, right?
It's not just about the deposit. It's like you have code in your account, in your smart account. Somebody else can call it. So in order to handle this, what do you think we can just add something to the implementation? What do you think we can do?
We can
require statements here.
Sender.
Yeah. Message.sender gonna be equal to what do you think it is? And this is what I like about this actually.
Yeah, I mean, it's gotta be someone that we allow. It's gotta be someone that we allow to interact with Bob's smart wallet.
And who you guess it is? Who you guess it is? Like right now, because
maybe
think about installation. Have a dream inside a dream.
I don't know. I guess it's not tx.origin because that would be. Oh, it's gonna be himself.
Yeah. So now what's going on? This call is actually coming from itself, like, and I will show you that in Etherscan. Like you can find it like from and to are the same address. Can you imagine this? You have your wallet. You say I need a transaction.
This is the one.
BitKey.
There's a big problem with Flash ears when doing that, right? I mean, even OpenZeppelin, they did the do not self-call for some smart contracts.
I think we need. Well, in general, actually, this new update requires to relook some other implementations. And actually, I throw that also in the CTF. If you are using, for example, message.center that equal to TX origin, because you want to emphasize that the caller of the function is has to be an externally owned address, it doesn't apply anymore. So there are things out there that should change. So maybe we need to look also at the flash loans, look in depth what are the security implications. But this is one of the security implications right now. If you have this implementation inside your smart account, you need to be checking, emphasizing that, the caller is itself, because other people can call. So if I test that right now, you see, what do you expect? Yeah, it reverts, because I told you the caller here is not actually Bob, and I want somebody to pick it up. So this is like, you can imagine you have this code inside your smart account and somebody else calls it and you lose your money. We're going to talk a lot about being rugged and losing your money here, but that's one of them. So now, in order to make it successful, I'm going to say, hey, I'm going to be Bob. Bob now is the caller. So now it works, you see.
Nice.
I want to show some sort of like an example that's going to be close to what we can deal with in the real world. So that's why I chose something in the front end this time. So this is going to be the next one. But I want to like talk about something here. You might be thinking like about the smart contracts. Like what about the deal of this of this smart accounts now? Like now it's time to talk about this. Is it really a big deal? So I'm thinking about it this way, because when I read the posts from Ethereum, they are low key like thinking about targeting global adoption, So in order to do this, you need the best user experience. Right now, Web3 is not easy to deal with, like as normal other Web2 apps. Like this is actually something I think about a lot. If I'm gonna build my own project, I want to think about something like, hey, I want to attack the market of the Web2. So in order to do that, you need actually to provide a good user experience that is familiar to the Web2 users. And this update comes in the context of other updates. Like you can't see it alone. You need to see it with the account abstraction upgrade. You need to see it with something called 5792, which we're gonna see also. So like you imagine that guy that just barely knew about Bitcoin, and he took a day to understand like grab Bitcoin and dealing with wallets and stuff like that. He needs something easy to deal with. So now let's go walk to another example. I want to show you. Okay, I have a lot. Yeah, that one. Okay, so this is just this was just a simple Next.js template with some functions from Ethers and Web3. And I want just to focus on this part here. So how do you actually utilize this kind of function? There's another standard, and it's implemented by MetaMask. When you want to interact with your MetaMask wallet, you just send it one transaction, like to a certain smart contract or whatever, and it's just supposed to send it on chain. But this time you can see here, I'm actually having an interesting property called calls. These are not only just one call. Like this is what I want to focus on. And guess what? You have also here one of the, like you have two objects, and each object has a different address in which you interact with.
So I can increase allowance for several smart contracts at once, several tokens at once.
Yes, exactly. This is an increase allowance, which is like a proof. This is an increase allowance call, and this is an AVI call data. This is just a supply. Yeah, this is a supply call. So what you're having here, like here, I'm just giving, this is a call data. Like if I look at this call data, let me check. Set increase allowance. This is just a React app. Like this is the way they do their hooks. If you check this function, it's just an encoded function data of increase allowance with a spender and amount. So the spender here is Aave, and the amount is whatever amount of rep Bitcoin you want to send. So this scenario, I'm just going to Aave, and I say, I tell Aave, hey, I want to supply you with like 1 rep Bitcoin. And before I supply that rep Bitcoin, I need to approve it. This is basically what we talk about. So I'm doing this in my front end in one transaction. Do these both calls in one transaction. And you see another keyword here, atomic required, and I'm telling it true. This tells MetaMask, hey, I want this actually to be done from a smart account, in a sense. So if it's not a smart account, it should make it a smart account for me. And we will look deeper into this. So like, what do you think about this?
I mean, it sounds like you can have a lot of problems, just by being able of sending several calls at once. You can be authorizing things that you don't want to, and everything is done at one transaction, right?
Yes, it's a one transaction because now, as I tell you, your externally owned address is actually kind of a smart contract now. So
everything will happen automatically
inside. So it basically gonna transform your account, your wallet, your innocent wallet to become a smart contract, and then it puts this code in it. Increase allowance call data and Aave call data, and you executed both of them in the same transaction. So let's stop talking and let's see what's the deal. What is this actually is. So I'm gonna take care here. Oh yeah, that was a PNP. By the way, PNP is PNPM is really cool. Like it's much better than NPM. Inspires other people to use it.
What's the difference? You can change the version.
It's more cleaner.
Awesome.
But you need to look at more into the details. Okay, so let's take a look here. Yeah, let's ignore that. But hydration is just about synchronization between the server side and the client side. Okay, so I'm gonna connect my wallet. I need first to give it my very super strong password. If you like it, I don't care. Okay, yeah. Okay, so what are we actually having here? I make that button. This button is actually the code that we have here. So when you click on it, it sends those two functions to be executed in one transaction. So that's what we're gonna do. But as I tell you, in order to do that, my account has to be a smart contract first, which is called a smart account.
But it's
So
not like
you open MetaMask.
That one, that 0xA is a smart account?
Yes, that my account is a smart account. There are other accounts that are not smart account. Let me check them out first, okay?
Okay.
So if I use this account, for example, I think it's not a smart account. Yeah. Come on. Yeah. So like you click this in MetaMask. They did a lot of exciting updates. Like I use this device more than my laptop, and I have the older version of MetaMask, and they don't have this. So I think this is interesting. So you see here, this interface, account update. Now you have a standard account, but now you want to make it a smart account. So you basically need to have this first. Let's see what this alerts are. Yeah, you're editing your smart accounts. You'll keep the same account while unlocking. Yeah, that's cool. Okay, whatever. I'll confirm that. Ah, okay. So transaction is confirmed. Now it's a smart account. Okay.
Okay.
I want to check something. Okay, so when I told you it becomes a smart account, you expect to have some code inside it. So let's see what actually the code inside it in order to do this. Sorry, I need to, because this is the only thing I need in this command is the RPC. I cannot remember the RPC. So I want to peek into this account. I will just copy its address. Okay. I believe you cannot see it from here. Is my screen big enough? You can see this?
Yeah, we can see.
Okay. So what I wrote here is the command cast code and the address. This is my wallet. I connected to this RPC, which is just Sepolia RPC. So I'm telling, so I'm using cast now to say like, hey, connect with Sepolia, and I want to check this address. I want to see what code inside it. And you just saw now that I actually updated it. I put some code, and this is what it spits at me. So telling me, hey, this is the code inside this address, this account. So now let's analyze this. What actually this is. So if I go to Etherscan, if you look at this address here, you will find that, sorry, if you look at this supposedly code right now, you will find it's not actually all code. There is first section, this part, EF0100. This is actually kind of a preamble that tells Ethereum, hey, this is a smart account, and what comes next is not code. This is the address of an implementation. So it's kind of a delegation thing. Like, hey, if you want to have code, if you want to interact with the code inside this smart account, you need a kind of delegation to this address, which is the 63C0C0 whatever. So let's take a look at what's inside this 636 whatever. This is supposedly now the code that lives inside my address in a form of delegation. So this is a contract. You see, like there's a lot of things here. I need this bigger screen. Yeah, this is now implemented inside my smart account. So it is something actually done with MetaMask. I don't know who implemented that. I forgot actually. But it's something basically provided by MetaMask now. I just want to take a look at the execution, how it's done. I forgot that part. Yeah, this is execute here. Yeah, this is what we are interested in. So you see here, like if the call type is batch, which actually is the one that we are doing right now. We're having like a batch, which is like few instructions, and we are doing it in an atomic way. We want it to happen in one transaction. So what it does, yeah, I want to, yeah. It's actually implemented like a kind of a multi-call, and I want to get it like we're not gonna look at all these files here. I just want to look at the interesting part. I think it should be here. Let me search for it. Yeah, this one. This is actually the one. This is an execution helper. This is actually the code that executes in the end. Like I traced it until I reached this part. So you remember, like I sent a call data for increase allowance. I parsed it to become a call data, and I also have another call data for supply to Aave.
Yeah.
All these call data are just executions now. These are two, and it goes in a for loop to execute each one. With the target, the first target is the red Bitcoin, because I want to call the increase allowance on the red Bitcoin. And the second target is the Aave, which I call supply on it. So what I want to say, the code you are having in your smart account is not just like some code that does a specific thing, which is, for example, approve and supply, or approve and swap, or whatever. No, it does generic things. It's just a multi-call, basically.
Wow.
If you know what a multi-call contract is.
Yeah.
You can just throw in 10 transactions here, 10 call datas, and it executes them all like a sweeper.
So I can just like drain everything in the wallet at once.
That's dangerous. That's really crazy. You can think like, if right now the problem is not you're approving, you're approving some malicious attacker to take your tokens, to like transfer your tokens. No, you're actually just giving away your contract. Giving away your wallet.
Wow.
You're not just giving away, for example, your assets, your tokens, or whatever. You are literally giving away everything. It's like actually giving away your private key. So if that address is a governor for an important protocol, or an admin for some contract, he also gives away this, because this execution can be something generic. It can be anything. It can be called to the contract that you are governing. It can be anything. So it's basically you're giving away your private key. And I'm not saying that
very hard.
Yeah, well, this is something I'll show you, but I mean, like, I'm not saying that as if it's something I'm against it, but I actually mentioning these parts to tell people, hey, you gotta be careful. This is more than what you just think about. It's not just, hey, a smart account, cool thing. No, you gotta be more careful when you are updating your account to a smart account. There are a lot of things you need to think about. So let's do the interaction now, since I showed you this part. So to summarize, you like to remember the sequence. We updated our MetaMask account to become a smart account, and what MetaMask did is that it made this contract the implementation contract for our smart account, which is just a generic multi-call, can do anything. So where is it? Yeah. This part is a bit nuanced, so to speak. Sometimes it fails, sometimes it works. But I will show you like the important bit here. So now I'm connecting to this front end. Okay. This is what I like now about MetaMask. As I told you, like I have my other device, which is not, the MetaMask is not updated, and I don't see all this stuff. And actually the transaction goes smoother. It doesn't fail.
Interesting. Show all the transactions. One thing, it doesn't show what's the code there that does, right?
No, it shows. This is why I tell you I like it now. I will tell you like what's here. So you see what MetaMask is telling you. Like, well, man, this is not cool. It shows you an alert. It shows you here alert. It's not like a normal transaction right now. So you need to look at it, because someone giving you permission, blah, 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 whatever. I got it, because this is my, after all, this is my front end, and this is just a test network. But if you are interacting with some random protocol or some random website, Web3, and you're doing this kind of transaction, it will show you this, hey, take care. This is like a transaction that is going through the code. Like it can implement anything, like any number of calls in one transaction. So it just tells you this. And it shows you here the call data actually. It shows you here, hey, first call is an increase allowance. The older versions didn't show that, and I like this. I like this update. So it shows you here you're interacting with this address, which is, if you look at it, this is the red Bitcoin address. You need to look at this, and it tells you here you are doing an increase allowance call to this address, which is Aave. I'm approving Aave to spend my Bitcoin, and this is the amount. Transaction 2 it doesn't decode it, which, like it's a hit and miss. Something it can decode, something it can't. But it tells you at least what is the interaction. It doesn't tell you that you are doing supply, but yeah, this tells you something. So if I do confirm, like it's warning you a lot. The problem sometimes it even fails because of this, and I don't understand. Like, let's see if it fails or not. Like, sometimes it fails. I try it again. It succeeds. Oh, it fails. Okay.
Okay.
The older version, it succeeds just straight away. But let me show you. Let me do it again. If not, I'm gonna show you like the result. Yeah, you see, now it decodes it. As I told you, sometimes it's hit and miss.
Weird.
See? Now it tells you it's a supply. The second call is a supply.
Some sort of caching, maybe.
I don't understand. I need to check out how they do it, the implementation, but like sometimes it decodes it, sometimes it doesn't. When you think about it, it's because the function selector is a hash, of the function name and the arguments. So it does some sort of a search, like it should go to the contract and search for that function selector and get the implementation, like gets the source code or whatever. So it needs to get this supply. When you have a hash, you cannot reverse it. You cannot get the pre-image of that hash. So you need to search for it. So this search, maybe sometimes it hits, sometimes it misses. So I'll do now confirm. If it doesn't show it, I will just go to Aave. And yeah, now it succeeds.
Nice.
I don't know. I think like maybe I'm wrong, but I think it's a kind of a safeguard. The transaction seemed to fail when it didn't decode this part, when it didn't decode the second transaction. That's something I don't know. But what we agree on right now, there needs to be a lot of safeguards, right? And it seems they are doing their job regarding this, right? What do you think?
Yeah. Let's see.
So yeah, you see
Here
here,
we go.
I did like this is Aave. I did the approve and the supply in the same transaction, and now I have some deposit in the Aave vaults, like in Bitcoin, as the example says. So yeah, by the way, like I need to mention this also. Like this is if you want to look into some details about this MetaMask construct, the send calls. You can find it here. It's part of the standard called EIP 5792. And as you remember, I told you, like, you have these actually things working together. You have EIP 7702, you have EIP 5792, whatever. You have account abstractions. They want to make it together, like with one goal, which is to change the user experience, to make it much easier to interact with Web3 protocols. So, like, this is basically where I actually got. Yeah, this is basically where I got the codes, the calls, and yeah. So it has some security implications. I didn't mention a lot of things regarding security because there are a lot that actually deserve its own session. But there is a CTF. I hope anybody here can try to play with it. And this CTF have something related to smart accounts, EIP 7702, in which you can use to find an exploitation in the contract. Like before EIP 7702, you wouldn't be able to exploit that contract. But now with EIP 7702, you can exploit it. So that's something.